We say that a continuous rotation is proper if all points under that rotation either move clockwise without ever backtracking onto themselves, or counterclockwise without ever backtracking onto themselves. So what do I mean? Well, this would be proper rotation. So this would be proper rotation. If the trajectory of a given point was like this, that would correspond to a proper rotation. This would be proper rotation. So this would be proper as well. So you can see a point made a full circle and then backtracked a bit onto itself, but without ever changing direction. And this would be non-proper rotation. So non-proper rotation would be something like this. We start onto a regular circle, but then suddenly here we change direction and we go back a little bit, and then now we go in the opposite direction. So this would be non-proper motion. Okay. The radian measure of rotation is a number with the following properties. It is a number that has sign. It could be either positive or negative. First, let's speak about the magnitude of the measure of rotation. The magnitude, so the absolute value, so the magnitude of a rotation, that's equal to the length of the arc traversed by a point under the rotation. So I'm taking an arbitrary point A, and I'm measuring the length of this arc, the arc that's traveled by A under the continuous rotation. So I'm taking the length of that arc, and I'm dividing that length by the distance between the point and the center of rotation. So this is my radius here, my number r, that's the distance between the point A and the center of rotation. So that number r, I'm dividing by it. So the radian measure of a rotation is given by taking the length, so measure of rotation, so that would be the length of the arc AB divided by the length of the radius r. So think of something like this. Say, for this particular example, we could have, think of this as something like, so an example of that would be, for example, something like a 5 centimeters arc length divided by 2 centimeters in the radius. So that would be the length of my radius, and that would be the length of my arc. Okay, so we found out the magnitude of the measure of rotation. What's its sign given by? The sign of the radian measure is taken to be negative if the rotation is clockwise, and if the rotation is counterclockwise, the magnitude of rotation is given a positive sign. So this would be given this would be a positive rotation, and if we're rotating in this direction, that would be taken with a negative sign. The radian measure does not change when we change the point whose path length we're measuring. See, in the beginning, when we started this definition, we said, well, kind of pick an arbitrary point A, right? And then with that point A, measure the length of a certain arc, measure the distance between that point A and the origin, and then divide the two numbers. Well, maybe we would have gotten a different number had we chosen a different point A. Well, the claim here is that it doesn't really matter which point you choose. If you remember, the arc length traveled by a point under rotation, it doesn't really, it is proportional to the radius, to the distance between the point and the center of rotation, right? That was that theorem about the concentric circles and the arc lengths cut off by geometric angles and out from those concentric circles. Okay. here's an interesting point to be made. So if I take a measure of rotation, it would be the length of a certain arc divided by the length of a certain radius. Both of them would be measured with the same measurement units. Say, for example, here I use the centimeter measurement unit. You could cancel the two measurement units. In this particular case, say, with these made-up numbers, I would have gotten something like 2.5. Now, what's the measurement unit of an angle? Well, since I cancelled the measurement unit of centimeters here and the measurement unit of centimeters there, this is unitless, no units. So it seems that angles do not have units. So, radian measure of rotation has no units. But if you recall, when we're defining a measure of a geometric angle, this was given as this was a certain length, if you remember. It was given as a certain length. Length, that was a length, let me be more precise, that was the length of an arc of the unit circle. If you remember that since this was an arc of a circle, it was always between 0 and 180 degrees, right? Because we're length actually of the short arc of a short arc of a circle. Because we were always picking a short arc of a unit circle, that arc had always length less than or equal to pi measurement units. So if you can see, so a thing to note is that the measure of a geometric angle, it appears to have units. So it has units, measurement units. Whereas radian measure of continuous rotation has no units. So if you hear the discussion of whether rotations or degrees have units, the answer is they both do and they don't. So if we use angles to measure rotations, you cannot speak of units. And if we use angles to measure arcs of geometric angles, you could speak of measurement units. So in other words, there are no errors. It depends on context. So whether degrees can be assigned a unit or not, it really is a matter of definition, if you wish. Okay. The radian measure of rotation equals the signed arc length traveled by a point at distance 1 from the center. Right, because if you take the distance between the point A and the origin O to be equal to 1, then if you take the length of AB, and you have to divide it by the length of R, but that's the length of the arc AB divided by 1, because we have selected R to be equal to 1. So we're getting simply, when we divide something by 1, we're getting simply the length of the arc AB without the units. The units have cancelled. So this one had units here, this one had the units as well. So here I've omitted the units, but if there were units, I would be cancelling the units here. Okay. So in that way, since a circle of radius 1 has circumference 2 pi, a full counterclockwise turn is measured by 2 pi radians. So a full counterclockwise turn is 2 pi radians.